Welcome to Study Loop.
So here it's asking us to find the mean free path, and they're just giving us a lot of the uh, the givens. So let's write them down. P equals 3.50 times 10 to the negative 13th. So what's the mean free path of these molecules within this evacuated chamber? This is approaching a vacuum, 10 to the negative 13th atmosphere. That's a very low pressure, easily obtainable in a lab. However, again, it is approaching a vacuum. So we have T equals 300 Kelvin. And then we have radius equaling 2.0 times 10 to the negative 10th meters. So that's the radius of one molecule. And then we're going to use an ideal gas constant that may not be the most familiar. So it'll be 8.2057 times 10 to the negative fifth. And I'll write down the units. So this is going to be meters cubed atmospheres Kelvin to the negative first times mole to the negative first. So it'll be meters cubed atmospheres per Kelvin per mole. And then we can simply find there's a mean free path, lambda is going to be equal to RT, and then 4 radical 2 pi r squared, Avogadro's number, pressure. This is simply a formula, but at this point, because they're giving us all of the constants, we only need to plug in our constants and solve. So again, we have lambda is going to be equal to 4 radical 2 pi r squared, and I'm just doing the bottom in order to save as much space as possible. So we'll have 4 radical 2 pi, and then 2 times 10 to the negative 10th squared. Avogadro's number, 6.023 times 10 to the 23rd. And then our pressure of 3.5 times 10 to the negative 13th. And then RT. So on the RT would be our numerator. Okay. And after you solve for this is going to be equal to 1.64 times 10 to the 5th meters. And this is really high. So what the whole idea of even creating a vacuum is so that you can, when you create a vacuum and you deliberately send molecules or, protons, electrons, whatever you may be sending through the vacuum serves as a free space. So when it says mean free path of air molecules, that means that an air molecule has to travel 1.64 times 10 to the 5th meters. That's an average. So the average length before it hits another molecule. So that's really important because when you're firing electrons in a microscope, when you're firing electrons at it's scanning electron microscopy, you're firing electrons at a sample. You need to fire electrons to the sample in a vacuum, because if the electrons were not in a vacuum, the mean free path would be so low that the electron is bound to hit another molecule before it actually hits the sample. So by creating a vacuum of 10 to the negative 13th atmospheres, you can fire electrons at a sample, and the electrons are sure to hit the sample. Without hitting any other molecules, because the vacuum is truly evacuated. And then you can calculate the mean free path. So here, 10 to the 5th, that's a very high order of magnitude in terms of a mean free path. I mean, one would have to travel around 10,000 meters or 10 kilometers in order to hit another molecule. So that's why vacuums are even created in the first place. So rather one reason why vacuums are created in the first place. So again, this would be our final answer. And that's the end of the solution. Thank you for watching.